Hello and welcome to this Revision Monkey video on Physics Paper 1 required practicals. The first 5 are for combined and separate scientists, and the 6th practical is for separate scientists only. In this practical, you'll be calculating the specific heat capacity of a material. And the specific heat capacity is the energy needed to heat 1 kilogram of a substance by 1 degrees C. Now there is an equation to go with this practical, and this equation you're actually given on your data sheet. The equation is E equals m times c times theta, whereby E is energy, measured in joules, m is mass, measured in kilograms, c is specific heat capacity, measured in joules per kilogram degrees C, and theta is temperature change, measured in degrees Celsius. So the good news is that you don't have to learn this equation. They will give you this one on the equation sheet. However, for this practical, we are going to be calculating specific heat capacity, which is the C part here. Therefore, we need to somehow work out the energy transferred to our material, the mass of our material, and the temperature change. And I'm going to take you step by step through the practical. If you find this practical particularly challenging, I'm going to take you through a simpler method first of all, and then after this a more difficult one using several equations. So you may want to skip forward to that one if you prefer, or if you'd like a much simpler method, then have a look at this one. So let's say, for example, we have this metal block. That is the material that we want to measure the specific heat capacity of. In the exam, it could be anything like aluminium or copper, or they could talk about a random substance altogether. So the first thing we do is weigh the metal block using a balance and record the mass. So this will give us this part of our equation, the m, the mass. Then we need to wrap our block in insulation to reduce the energy transferred to the surroundings. So you might have some bubble wrap or something like that you would wrap your block in. Next, we place a thermometer in the block, and we need to measure the temperature of the metal block using the thermometer and record it. So this is our starting temperature. We measure our temperature of the block. We then put an immersion heater, which is this heater here. We call it an immersion heater because you put it inside the substance, you immerse it in the substance. We need to plug that into a joule meter over here, and then plug it into a power supply. This joule meter here will give us our energy transferred to the block. We place the immersion heater inside the metal block and start a timer. Next, we heat it for 10 minutes, and after 10 minutes we read the temperature from the thermometer and record it. And we use this then to calculate the temperature increase. Temperature after minus temperature before gives us the temperature increase. So now we have 3 values which we can use to calculate the specific heat capacity. We've got the energy that we've got from the joule meter, we've got the mass which we've recorded on the balance, and we have our temperature change which we've recorded using the thermometer. So the final thing we need to do is rearrange that equation on our data sheet to make it specific heat capacity equals, and that would equal energy divided by mass times temperature change. So to do that, we read the energy transferred to the block from the joule meter. That will give us the E like we said. And then we put the numbers into our equation. Specific heat capacity equals energy divided by mass times theta. Now I'm going to move on to a more difficult method that doesn't use a joule meter, which uses a couple of equations to work out the energy transferred to the block. So if you're comfortable with this method, that's great. You can skip to the next required practical. If not, you might want to listen up to the more difficult method, which is coming up straight after. Okay, so we're still on the required practical for measuring the specific heat capacity of a material. This method doesn't use a joule meter, but many of the steps are the same as the simpler method. Again, we're going to focus on this equation on the datasheet, E equals mc theta, which we can rearrange to calculate specific heat capacity. So we still do the same steps as before. Weigh the metal block using a balance to record the mass. Wrap the block in insulation to prevent heat transfer to the surroundings. Place a thermometer in the block to measure the temperature before. The next step is slightly different, however. This time we're going to plug an immersion heater into a power supply and connect an ammeter here in series to measure the current. We're going to then place an immersion heater inside the metal block and start a timer as we did previously. So rather than a joule meter this time, we've got an ammeter. We're going to heat it for 10 minutes like before, and after 10 minutes read the temperature of the block and calculate the temperature increase. So we've got mass like before, we've got theta, temperature change like before, and what's different is how we're going to calculate energy. So if we've calculated current, you need to use the equation for power. P equals I times V, where I is the current, which is read from the ammeter, and V is the potential difference that you set on your power supply. So using this equation here, we can calculate power by multiplying the reading from the ammeter by the reading that you've set on the power supply for potential difference. Next, we need to use a different equation to calculate energy transferred. That equation is E equals P times T. So P we've calculated from this equation above, and time in seconds is the time that the immersion heater was heating the metal block for. And the final step is then to put it back into this equation. Specific heat capacity equals energy that you've calculated from the two equations divided by the mass times by the temperature change. How does the length of wire affect resistance? Required practical. For this required practical, we need to recall the equation V equals I times R, whereby V stands for potential difference measured in volts, I stands for current measured in amps, and R stands for resistance measured in ohms. And because we want to calculate resistance, later on we'll use the rearranged version of this equation to make sure we've got resistance equals V divided by I. So in this practical, we need to change the length of the wire. That's going to be our independent variable, and we are going to measure resistance, which will be our dependent variable. So the first thing we do is set the power applied to a specific voltage, for example 6 volts. We will connect 2 wires to the power supply and add a crocodile clip to the other ends of the wire. We'll then add an ammeter in here in series, and this will measure current, which is going to be the I part of our equation. We will then attach a length of wire to a meter ruler, so on the ruler like shown, and clip one of the crocodile clips at the 0 centimeters mark. We'll then attach the crocodile clip of the other wire at the 10 centimeters mark, so that the length of wire in the circuit is set to 10 centimeters. We then need to add a voltmeter parallel to the length of wire that we are measuring, and this is going to measure potential difference. We turn on the power supply and record the current from the ammeter, which will give us I. We will record the potential difference from the voltmeter here, and this will give us our V. And finally, we use the equation R equals V divided by I to calculate the resistance across the 10 centimeters piece of wire. To change the length of wire we are measuring, we'll keep the first crocodile clip at 0 and move the other one to 20 centimetres. And then we will repeat as before, taking the readings for current and potential difference and using the equation R equals V divided by I. Now you need to suggest the range of lengths that you are going to use in the experiment and you need to list them out. For example, repeating the steps above for the following lengths: 30 centimetres, 40 centimetres, 50 centimetres, 60 centimetres, 70 centimetres and 80 centimetres. And then what's really good to do is end by saying that you're going to repeat the experiment by calculating the resistance for each length of wire 3 times and calculate a mean. And if you were to plot a graph of your results, the results that you should see are that as the length of wire increases, the resistance also increases, and a straight line through the origin shows you that the relationship is directly proportional. Resistors in series and parallel, required practical. In this required practical, you are asked to investigate how adding resistors in series circuits or parallel circuits affects the total resistance. For this practical, you also need to recall the equation V equals IR, whereby V stands for potential difference, I for current, and R for resistance. This here is the resistor. I've drawn a circuit here with 2 cells. It may well be 3 cells or 4 cells, or you may have a battery. It doesn't really matter, but something to provide power to your circuit. And you're going to want to attach a voltmeter to measure V, an ammeter to measure I, and you're going to use a calculation to calculate resistance. So we set up a circuit with, suggest 2 cells, an ammeter to measure current and 1 fixed resistor in series. We connect a voltmeter across the cells to measure potential difference. And we calculate the resistance of the circuit using the equation R equals V from the voltmeter divided by I, which is current from the ammeter. We then add a resistor in series, and when we do this, we're adding the resistor next to the first resistor in exactly the same loop. So we add a resistor in series with the other one, we take new readings for potential difference and current, and then calculate resistance. We will then add another resistor in series with the other two, and again we will repeat the steps to calculate resistance. So if you did add resistors in series like so, you should find that as you add the resistors, the total resistance of the circuit increases. So you might get a graph that looks a little something like that. In fact, the total resistance is actually the sum of all the resistors. So for example, if these were each 5 ohms, our total resistance in the circuit would be 10 ohms. So you can do exactly the same practical, but this time for a parallel circuit. You would start with your initial circuit with 1 fixed resistor, measuring current, potential difference, and using the equation R equals V divided by I as before. But this time you would add a resistor parallel to the first resistor, which will put it in its own separate branch. Again, you'd measure the readings and calculate resistance, and you'd want to add another resistor, again parallel to the other two, and calculate resistance using the potential difference and current readings. However, in this case, with parallel circuits, you should find that if you add resistors in parallel, the total resistance of the circuit actually decreases, because you can think of it as providing alternative pathways for the electrons, which therefore allows the electrons to flow more easily around the circuit. So in this case, your relationship would be as the number of resistors increases, the total resistance actually decreases. IV graphs required practical. You may well have heard of these called IV graphs or current potential different graphs, with the I standing for current and the V for potential difference. So with these graphs, the circuit that we need to build is all the same. And what will be changing is this component here. At the moment, we've got a resistor in the circuit, and we need to be able to change this for a diode and then a filament lamp. So we set up a basic circuit with either some cells or a battery, an ammeter to measure current, a voltmeter to measure potential difference, and this component here is a variable resistor. This allows us to change the resistance of the circuit and therefore the current. So we're going to start off by looking at a circuit to draw an IV graph for a resistor. So our end goal is to be able to draw a graph of current against potential difference and plot all of our results on our graph. To get there, what we need to do is set up the circuit. I've just suggested 2 cells. You might just put a battery in there, or just 1 cell, it doesn't really matter. An ammeter to measure current and a variable resistor. And we're going to start off with a resistor in series. That's just the component that we're looking at. We then connect a voltmeter parallel to the component to measure potential difference. We take the reading for current, which is going to be our I, from the ammeter, and take the reading for potential difference, which is going to be our V for the voltmeter, and plot these on a graph of current against potential difference. You may well say that you're going to put them in a table first and plot them later. Either is fine. We're then going to adjust the variable resistor, which is this component here, and take new readings for current and potential difference. And we're going to repeat this 5 times. So if we adjust this 5 times, it will give us 5 sets of readings for ammeter, which is the current, and 5 sets of readings from the voltmeter, which is potential difference. If we didn't have that, we just get 1 reading from each and we would be stuck. So this gives us a wide range of readings. Up to this point, we would have been able to draw this part of the graph, whereby we've taken readings for current and potential difference, and we've plotted them and drawn a line of best fit. However, we also need to get the negative region of the graph, so we do that using the next step, which is to remove these cells and to replace them into the circuit in the opposite direction. And then we repeat steps 3 and 4 above. And by doing that, we get negative readings for our voltmeter and ammeter, and we can collect data for this negative region of the graph. So that's our completed graph for a resistor at constant temperature. You can see a directly proportional relationship between current and potential difference. If we wanted to replace this component and investigate something else, that's all we would have to do. We'd leave the rest of the circuit the same, and we can replace it with a diode, for example. Now, a diode only lets current flow in one direction, so you'll notice that the graph does not have values in the negative region, and it only has values in the positive region. Finally, you might want to draw an IV graph for a filament lamp, and this graph has a different shape again, because as current increases, the temperature of the filament lamp also increases, so resistance increases. Okay, you can see here the graph tailing off as current gets higher. The trouble is the lamp gets very, very hot, and then the atoms in the wire vibrate more. They are already vibrating because they're a solid, but they vibrate more, making it more difficult for the electrons to flow. So we get this curving off here as the resistance gets really high, so current can't increase at the same rate that it was before. Density of regular and irregular objects required practical. For this practical, we need to recall the equation density equals mass divided by volume, whereby density is measured in kilograms per meters cubed, mass is measured in kilograms, and volume is measured in meters cubed. So if we start by looking at the density of a regular object, here I've got a cuboid. We would measure the length, width and height of the cuboid using a ruler and convert each measurement to the standard unit, which is meters. Multiply the length by the width by the height to calculate the volume in meters cubed, and then we place the object on a balance and measure its mass in kilograms. We finally calculate the density using the equation density equals mass over volume. For irregular objects, we again need to calculate the mass by placing the object on a balance and measuring its mass in kilograms. To find its volume, however, we need to fill a eureka can, or you may call it a displacement can, with water, until it is level with the spout. We will place the Eureka can on a tripod and gauze, and we will place an empty measuring cylinder below the spout. We will then place the object in the can and measure the volume of water displaced into the measuring cylinder and convert this to meters cubed. So then we can put our mass into our equation, divide it by our volume, and we will therefore be able to calculate the density in kilograms per meters cubed of the irregular object. Heat insulation required practical, and this required practical is for separate scientists only. So to start off, we'd boil some water, and then we'd measure, for example, 200 ml of water using a measuring cylinder and pour it into a container. We'd record the starting temperature using the thermometer. We then wrap the container in an insulating material, for example wool, and place a lid on top of the container. We'd leave it for a set amount of time, for example 10 minutes, and then we'd take a new temperature reading and calculate the temperature decrease of the water. The most effective insulator will be the one that has the smallest temperature decrease. We then repeat it with different types of insulation, for example bubble wrap, foam, cotton, etc. And we repeat it 3 times for each type of insulation that we're using and calculate a mean temperature decrease. Now for this experiment, our independent variable was our type of insulation and our dependent variable was our temperature decrease or our temperature change. Now in the exam they might ask you to investigate a different independent variable. For example, rather than the type of insulation, they could get you to stick with one type, for example our wool here, but perhaps investigate the thickness of the insulation and how that affects the temperature change. So in that case you'd start with a thinner piece, do your readings, and then repeat the experiment with a thicker piece of wool, calculate temperature decrease, and again change the thickness again, and so on. So be resilient in the exam. They might not ask you for different types of insulation, they might ask you for something like changing the thickness instead.